Okay, so I think I have the easiest job in the world because our next speaker doesn't need any introductions. We all know Professor John Dolbow. Professor John Dolbow is a professor of mechanical and material science at Duke University, and he's also right now the associate vice president for research and innovation at Duke. And I think Professor Dolbow has many achievement award, including the Young Investigator Award from both the USNCCM and the IACM. He also has the visiting professorship at Harvard, Okinawa Institute of Science and Technology, Sandia National Lab, and of course, he also serving us as the Secretary General of the IACM. So without further delay, let's begin the talk. Thank you so much, Professor John Dolbow. Thank you.
Let's see, am I mic'd up? You can all hear me okay? Okay, thanks Steve for that very kind introduction. It's an ambitious title. I'll try to honor it, okay? So before I get started, I just want to mention that much of what I'm going to talk about today is the result of a very fun and productive collaboration between my team at Duke University and Oscar Lopez-Paimi's team at Illinois. This started back in 2020, right in the middle of the pandemic, and we're very thankful for the funding from both NSF and NIH. And I'll try to acknowledge the contributions from the students in particular as I move through the slides, okay? All right, so what's our ultimate objective? Here it is in a picture, right? We are in the business, I think, of developing computational models. And in computational fracture mechanics, we want to describe lots of things, right? The idea is that we're interested in understanding what the equations are, getting the equations right, because if we have the equations right, we have some understanding of our ability to discretize them. Right, so in general, we have a structure with some arbitrary geometry. It can have some pre-existing cracks, both large and small, can have some sharp corners subjected to load. And what we want is that those equations describe the deformation of the object, the nucleation of cracks, and the propagation of cracks in the structure for any applied loading, right? And so that's our business. This is computational fracture mechanics in a nutshell. And over the years, over the past 50 years, we've developed a wide variety of models, methods, and algorithms for treating these problems, right? We know some of them by name: mesh-free methods, paradynamics, XFEM, GFEM, and phase field, okay? And I think if we're being fair, right, we'd all admit that mostly we have focused on the question of what happens to large pre-existing cracks, right? When do they propagate and where do they go? And we've given short shrift to the other question that's perhaps more important, which is when do cracks first appear in the first place, right? And where do cracks nucleate, right? So what is this lack of attention on this nucleation problem gotten us? Well, fractures and failures continue, right? So these are all examples from the past 5 years. This is from a Boeing 737 pickle fork. Boeing has been in the news recently for all the wrong reasons, right? You can find reports they just crack at only after 10,000 cycles, so much earlier than expected, okay? Some of you probably saw the news reports of wind turbine blades on offshore wind turbines breaking off and washing up shore, right? Composite fracture remains a very challenging problem for us in lots of ways. Some of you who are Formula One fans might remember Max Verstappen's very bad, no good day at the race in Azerbaijan, where one of his tires failed very unexpectedly, and Max was not a happy camper that day because he lost the race, okay? This is an example some of you might have seen from social media. I think given the year that we've had so far, Perhaps not surprising that the F key is the one that's broken here, okay? But the point is that these are all problems where cracks didn't exist from the beginning, right? They just appeared, okay? And so either our tools and methods and codes are not being used properly, or they're not terribly predictive, right? And I would argue that one of the issues is that we have mostly been building models that can be calibrated against particular experiments, right? Give us the experiment, tell us what happened, we can reproduce it. We'll figure out a way to do that, okay? Rather than building models that are actually predictive, okay? So I'll try to get at why that might be the case today. All right, so just a brief outline. I'm going to focus on probably the simplest class of materials, so I'll define that for you, namely elastic brittle materials, simple but not too simple, okay? I'll talk about some of their key ingredients and their interaction. This will lead into a discussion of some of the pieces that existing models have been, right, from my standpoint. Then I'll talk a little bit about a complete model, show some comparisons to experiments and extensions of that. And I hope I have time to tell you about the 9 circles of elastic brittle fracture and provide a summary and look ahead. All right, so what I'm going to be focusing on today, again, is really the simplest class of materials. Those are nominally elastic brittle materials. Okay, so what do I mean by that? This is basically an assumption, right? So these are materials that do one of 2 things when we subject them to loads. They either deform, and they deform elastically, or they break, okay? And so when we think about materials that qualify, many of us would think first about hard ceramics, okay? So this is an example of graphite components, okay? But this definition actually applies even more so to soft materials, okay? So this is a polyurethane elastomer, right? And once again, you know, this is a very good assumption for how this material responds, right? It does one of 2 things. It deforms or it breaks very suddenly, okay, when you put enough forces on it, okay? So sure, the deformations are finite. They're still elastic, right? And so according to this definition, this qualifies. The same is true for natural rubbers and synthetic rubbers, okay? So what we know at this point is that for elastic brittle materials, there are 3 intrinsic macroscopic properties that govern fracture nucleation, the first appearance of a crack, okay? They're the elasticity of the material, its strength, which I'll define here in a moment, and its intrinsic fracture toughness or critical energy release rate, GC, okay? All right, and importantly, these are independent macroscopic material properties, and we can tie each of them, okay, to particular experimental observations, all right? So what do we know experimentally, right? So again, we're in the business of writing equations. Those equations should explain observations, right? So what do we know experimentally? Turns out quite a lot. Of course, we know a lot about the mechanics of deformation as governed by elasticity. We also know a lot about the nucleation of fracture and its propagation, right? So and finally, the mediation between strength and energetics, okay, that applies to a wide range of cases. So I'm going to talk about strength and energetics and how they interact, all right? Okay, but again, I just want to emphasize that our focus, most of the focus from theoreticians and computational mechanicians over the past century really has been on the energetics piece, right? Starting with the work of Griffith, right? Really 3 and 4, with strength and its interaction with energetics largely being ignored. All right, so going back to the history, mechanics community has been subjecting materials to forces until they break for a very long time, right? And this goes back to early work by Gabriel Lemay. It's summarized here in Love in his famous treatise on elasticity. And this was mostly subjecting materials to uniaxial tension, right, until they break, right? Why were they doing this? Because we know the equations of elasticity hold, but only up to a point, right? And so the idea was that there's a critical value of tension, at which point the material breaks. And already this insight, this is a material property, okay? This is mostly for hard, but it was also done for soft materials. Okay? Some of you may know Stephen Perry. He's the inventor of rubber bands. Okay? And we've surely all played with rubber bands until they break. Okay? Sometimes painfully, right? But this general idea, in fact, applied with hard and soft materials for a long time. Now, fast forward to modern times, okay? More recently, this is what it looks like where we change things from uniaxial loading to multi-axial loading, okay? So what do we see experimentally? So this gives you some idea. Okay, these experiments are not easy to do, but you can find them. These are experiments on graphite tubes where the tube was subjected to an internal pressure, but then also loaded axially, right? And this allows the modulation of the principal stresses, right? It's a relatively thin tube, right? So it's basically plane stress. And the idea is that by adjusting the pressure, right, you can load up, right? You start at 0. This is the plotted principal stress space until you hit a point where all of a sudden cracks appear, right? And importantly, over the gauge section, the stresses are spatially very uniform, right? So again, this is a system with no pre-existing cracks, right? And you load it gradually until it breaks, and you record that point on this plot, right? So these are all the experimental data from this paper, okay? And what we can see is that, in fact, the set of these critical stresses defines a surface in stress space, okay? Now, experimentalists know this, right? This information, for whatever reason, simply hasn't been incorporated into a lot of our models with any kind of fidelity, okay? For whatever reason, right? In fact, the definition of strength didn't exist until recently, as best we can tell, right? Given by this definition, right? The set of all critical stresses at which the material fractures when it's subjected to a state of monotonically increasing but spatially uniform but otherwise arbitrary stress. And Oscar and his group deserve a lot of credit for introducing this definition and really emphasizing strength when it comes to fracture, okay? All right, so I mentioned the modeling work. What do we do typically? Right, a lot of existing models simply aren't designed to reproduce even these basic experiments, right? So this experiment has existed, we've known about it since 1985. It's only been reproduced within the last 5 years, okay? Right, and so what we do typically is at best we'll use information like the uniaxial tensile strength, right? That's those green circles on that plot as an input to our model, okay? But there's a lot more information here, right, that we haven't been making use of. And that's part of the reason why we've been calibrating things instead of building models that are genuinely predictive. All right. So that's strength. Now I want to talk about, just a few more comments before I get to Griffith. So how do we understand strength? What is it physically? It's at the macroscopic level, it's a material property. And it's the manifestation of the presence of microscopic defects, right, the weakest links of the material. It's independent from its elasticity, and it's independent of its fracture toughness, okay? So this is something you have to measure for the material, and it's a material property. And the strength surfaces can be quite arbitrary, right? All we know is that they're star convex, okay? But in stress space, they need not be convex, right? And so these are examples on a synthetic rubber, a sheet, again, plane stress, subjected to biaxial states of stress, okay? And because of the presence of the microscopic defects, the data has a stochastic element to it, right? So each of the experiments, there's some distribution there. But what you can see here, for example, is that this is a material where the uniaxial tensile strength is actually quite a bit higher than the biaxial strength. Right? So real materials, again, these surfaces can be fairly arbitrary. All we know is that you can't cross them twice as you're loading outward, right, from a zero stress state. Okay. So that's strength right on one end. Uniform states of stress, no initial cracks. When does it break? Okay? Griffith was focused on a very different question. okay? Griffith, in his famous experiments on glass bulbs, okay, that were pre-cracked and then once again pressurized, but there was a large pre-existing crack on the surface, right? And what we know from elasticity theory is that the state of stress ahead of the crack tip exceeds the strength, right, as soon as you apply any load, okay? So strength does not explain what happens here, okay? And so Griffith realized that he needed something different to describe when does that crack first propagate? When does nucleation at the front of a large pre-existing crack occur where the stress gradients are very large? Okay? And what he developed that explains his observations, right, is this idea of a competition of energies. Right? The crack grows when there's enough energy available through the decrease in the strain energy or the total potential energy, if you include the body forces, the tractions, okay, that is equal to a material parameter of the fracture toughness. Okay? And by the way, these experiments were done on hard materials, right, glass, but analogous experiments have also been done on soft materials. Right? So experiments were done on natural rubber by Boos, and Rivlin and Thomas later on used these same ideas and demonstrated that they can explain the observations, right, for both hard and soft materials when you have a large pre-existing crack. Okay? Now, this equation only tells you when you reach criticality. Right? Once you start up and running, you don't know where the crack goes. Okay? That didn't come until fairly recently, right? And this seminal work by Frankfurt and Marigo, which is essentially recasting Griffith as an energy minimization process, right? And what you obtain from that is both the deformation and the crack set, right? So you get the crack path out of this minimization process. Now, I'll notice here that strength is nowhere to be seen in this expression, right? Because it wasn't designed to be, right? It was designed to essentially explain Griffith's observations, right, in a different framework, right? So we have the elasticity, we have the fracture toughness, but strength is not here, okay? So we have these two extremes, right? Strength explains when surfaces first appear, fracture surfaces under uniform stress states, right? And Griffith, the energetics, explains what happens when we have large pre-existing cracks where the stress fields are singular. Okay, those are the extremes. Reality is somewhere, in most cases, in between, right? So what do we know about what happens in between? Okay, so we don't have a quantitative expression in between, but we have qualitative expressions. So here we have qualitative information. So here I'm showing probably the simplest example to understand this, right? So this is just a single edge notch tension test, right? So the idea here is that you put a notch in the specimen and you subject it to far field uniaxial tension, and then you measure the critical stress at the boundary, right, at the far field, okay, when that crack begins to propagate as a function of the initial notch length, okay? And what you see is that, yes, indeed, and these are experiments, experimental data on SBR, synthetic rubber, okay, that when the notch size is sufficiently large, Griffith energetics explains the data, okay? However, as the notch becomes small, essentially what happens is that the notch size starts to approach what we might think of as around the same size as the defects of the material, right? So here we see strength start to enter into the picture, right, in that limit. What happens between the two looks basically like an interpolation between strength and energetics, okay? All right, so summing up, where are we? All right, so we have these three ingredients, right? Elasticity, strength, critical energy release rate. Elasticity is needed to explain, you know, it's really the precursor. It gets you to the point where things go off the rails, right? But the strength surface is also necessary, right, for the nucleation of fracture governed by strength, the mediation between strength and Griffith, and the critical energy release rate is required for nucleation from large pre-existing cracks and propagation as well. Okay? So here's the rub. Models that don't include these three macroscopic properties and they're independently or fail to recover any of those observations cannot predict crack nucleation. Okay? So there's a corollary to this, and this was a paper that we published recently with, this is joint work with Oscar and Gilles and Chris Larson, okay, where we made a very strong statement, okay? And I want to be precise here in terms of classical variational phase field models. What we're talking about is that we're talking about those phase field models that gamma converge to the Sharp model introduced by Frankfurt and Marigo, okay? So the original one is here, and it does that, okay? And in essence, the issue here is what I said earlier. Strength is nowhere to be found here, right? And what people have been trying to show is that, in fact, thinking about the idea of setting the regularization parameter epsilon to a material property, right? Thinking about it as a material scale, right? And tuning it to your uniaxial tensile strength. And you can do that, but then you're going to miss the rest of the surface. And that information is really important. Okay? So people have said to us, well, look, what about the splits, right? And we addressed those in the paper, right? These splits were first introduced to deal with the crack that they wanted to prevent interpenetration of cracks in compression, okay? They were later modified to introduce anisotropy in tension and compression. And of late, they've been used to try to bring strength information into the models. The problem is that the strength is subjugate to the elasticity and the fracture toughness, okay? Really a clue that this is not the way to do things is that there are at least 20 different splits that you can find in the literature, right, in 25 years. You would think that after a while we'd start to figure out that perhaps this wasn't the way to do things, okay? All right, and the easiest way to see this is actually to look in the first octant of stress space. So in the first octant of stress space, all of the principal stresses are tensile, right? And by and large, all of these different splits reduce back to essentially AT1, right? The original, one of the original models, okay, by the phase field, all right? And so what you see here is that in that first octant, if you calibrate the regularization length to the uniaxial tensile strength, what you find is that the biaxial strength that you get and the hydrostatic strength are subjugate to Poisson's ratio. So if you want to adjust the ratio of tensile strength to hydrostatic strength, you have to adjust nu, right? This is crazy. Nu has its own job, right? And what you can see here is that, in particular, as you approach the incompressible limit of nu equal to a half, the hydrostatic strength that you're obtaining is becoming infinite, right? So the model is suggesting that materials are infinitely strong if they're incompressible, and we know that this is not physical, right? Real materials, incompressible materials, don't behave that way. All right, so that's the bad news about classical variational phase field models. And by the way, it has implications for lots of other models as well because they simply haven't brought strength information into the picture, okay? And fortunately, there's an alternative, okay? There's an alternative way forward, and this is the complete model that was introduced back in 2018 by Oscar and Aditya Kumar and others, okay? And there have been several updates last year that you can find that have several key improvements. But in a nutshell, this is a model with two variables, right? A displacement field, the governing equations for the deformation being the macro force balance, and a phase field V that is an indicator for the crack geometry, okay? That's subject to a microforce balance. So there was a lot that went into the development of this model, but in the end, the governing equation is actually pretty simple and in many ways very elegant, okay? Because what it's doing is it's bringing into the picture what was missing in these models. It's bringing in an additive way an external microforce whose job is to enforce under uniform states of stress that you have nucleation when you reach the strength surface of the material. Okay, whatever it looks like, it's constitutive information, right? It's an input to this model, okay? And this delta epsilon here is a rescaling so that you still have Griffith energetics dominating for sufficiently large cracks, right? So it has all three ingredients, and it's built in a way that allows you to recover these observations. A couple of more remarks. One thing I'll make a note of, there's no split of the energy here, right, importantly. Okay, a couple of more remarks about the complete model. The key idea really isn't that it's a phase field model, right? I just want to emphasize that. The key idea is that this is a model that merges strength and energetics in a manner that lets them compete, right, so that we can recover these experimental observations that I mentioned before, right? Strength limit, Griffith limit on the other, and mediation in between. It was originally motivated by applications of some of these models to nearly incompressible materials, right? And this motivates why an energetic model, purely energetic model, is problematic, okay? Because if you take a nearly incompressible piece of material and you subject it to a hydrostatic state of stress, it can't deform, right? Because it's nearly incompressible. And so it can't build up any strain energy, right? And so purely energetic models predict that you'll have failure at an infinite value of the pressure. But again, real materials don't respond that way, okay? The results are insensitive to the choice of the regularization epsilon, provided it is sufficiently small. Here's, again, some calculations on that single-edge notched problem, where you can see it recovers Griffith on one end and strength on the other for sufficiently small notches. And as you reduce epsilon, you get to a point where things aren't sensitive anymore to smaller epsilon, okay? Right, so provided it's sufficiently small, okay? And so importantly, the limit can be taken with both strength and Griffith being maintained. It is not a purely energetic model, but it is variational, right? And what we've shown recently is that, in fact, the equations are well posed, and that's really all we should care about, right, as computational scientists, okay? The last thing I'll say is that there are no free parameters. Okay? The only inputs are the constitutive information, right? Okay. So this model has now been applied to a series of problems. These are some of them, right, for crack nucleation in both hard and soft materials, okay? So we've implemented this in two different codes, right? Phoenix and Raccoon, which is built on Moose, two different labs. The model works as advertised. Okay. So I'm going to spend a little bit of time talking about this middle one in particular here, which is known as the Brazilian test. Okay. So the Brazilian test has a fascinating history. Some of you might know this. Okay. It was introduced by Lobo Carneiro in 1943 for concrete. Okay. Lobo was given a very particular task. Okay. They had a church in downtown Rio de Janeiro that was at the corner of two busy intersections. They wanted to widen the roads, so they had to move the church, right? So the idea was to raise the entire structure onto rollers and translate it, okay? Apparently they had done this successfully in Europe, okay? Now, the sad story is that the church doesn't survive, okay? But the Brazilian test does, okay? So as Lobo had to use concrete because this was during the war and steel was prohibited, okay? And what Lobo discovered is that if you take concrete cylinders and you put them into compression, they split right down the middle, right? This is basically a Poisson effect, right? You're squeezing it. Concrete is a material that's very strong in compression, but very weak in tension. Right? And so this test is ideal for materials like that because they're difficult to load in standard uniaxial tension. Right? And you'll still find this used today. Here's a quick video showing some recent experiments, so you can find these on YouTube. It's a very brutal fracture. It happens very quickly. Right? Now, over the years, there have been a lot of debates about this. test, right? Now remember what Dolbow was interested in thinking about is that this is an indirect way to measure the uniaxial tensile strength, okay? The problem is that the state of stress in the center of the specimen, it's not uniaxial, it's actually triaxial, right? So it's tensile in the x direction, it's quite a bit larger in compression in the y direction, and then it's basically a plane stress type of condition in the third direction, okay? So lots of debate, suggestions that the test is only valid if fracture starts in the middle of the specimen. That doesn't always happen. The ASTM has apparently been arguing with itself about this test and how you should use the data. This is the maximum load at fracture. This is the expression for the measured tensile strength, right? These are the specimen dimensions, right? So just an update after 8 years. That's the most recent one. In fact, neither of these expressions is correct, okay? ASTM actually made things worse with that change, okay? And we have details of that in the paper. So what's going on here? Well, so with the complete model, because we can adjust the ratio of compressive to tensile strengths in the model, right, we can ask what happens, right, for materials that are relatively weak in tension or very strong, relatively strong in tension. So here's two different simulations. This would be for like concrete, right, where that ratio is about 20 to 1. There you see nucleation in the middle and it propagates toward the boundary. But as you increase the tensile strength, you start to see nucleation of cracks closer to the boundary where the loading is applied, right? And notice here that from the formula, there is a threefold increase in the value here, even though there's a fourfold increase in the tensile strength, right? So the formula is incorrect, okay? Unless you think this is a fiction, we have really good qualitative comparisons with experiments. Okay, these are on shale specimens. The one below has a higher tensile strength as measured by the experiment compared to the one above. Okay, and we have quantitative comparisons with 3D printed mortar. Okay, that show an excellent match. What about the formula? What do we do about this formula, right? Well, in fact, in both of these cases, what we discovered is that the state of stress in the center of the specimen is here. Okay, and it's about that. Even when crack nucleation starts in the middle or at the top, okay? And what we want is this, the uniaxial tensile strength, right? But what we're probing is here, okay? So the idea is that if you know the compressive strength, if you have a good estimate for that, right, you can extrapolate based on the test up to the uniaxial tensile strength. And this is the expression. It's a modification of the formula. And you can find the details in the paper, okay? But this is kind of patient zero for the kind of things that we're talking about because it's not strength, right, purely. The state of stress is not spatially uniform. The gradients are really high. There's no pre-existing crack, right? There's a mediation here between both strength and energetics, okay? All right, I want to highlight some other presentations this week. This model has been extended in lots of ways that I don't have time to get into, right? I'll mention the work by Oscar Lopez Paimes on viscoelasticity. Sobrance is going to talk about fatigue. Alexander is going to talk about building things from the bottom up, looking at graphene sheets, and the fact that now you have an orientation effect to the strength surface that you obtain. Bo Zhang's going to talk about thermal shock problems. Really interesting experiments that have been studied by the community. A heated disk on the inside. In a notch case, the crack propagates straight across. In the intact case, it propagates in branches. The question is why, right? Lots of people have reproduced this with, again, calibrating things. But as far as we can tell so far, there's no explanation as to why, in this case, it grows straight across. And in this case, you have it first grow and then branch. Right? So we think we have an explanation. I'll leave it to Bo to tell you about that. Okay, I won't steal her thunder, but it probably won't surprise you that the explanation consists of both strength and energetics. Okay? The last thing I'll mention is that as we're pushing these models, right, incorporating, again, building complete models, incorporating strength into the picture, we start to reach problems where the mesh deformations are significant, right? And so having to rely on adaptive remeshing and total remeshing in order to be able to investigate the models, particularly for ductile failure, where the shearing can be really significant, right? All right. All right, so I'll just mention some of the work we've done on dynamic fracture as well. I talked about this morning. Really good experiments, comparisons. This is the dynamic version of the Brazilian test. There, once again, you see crack nucleation start in the middle and propagate towards the boundary for this particular experiment. There were some impact experiments on soda lime glass. We get quite good comparisons with experiments there. This was a recent CFRAC benchmark, so a relatively new problem. Okay, so there we were able to get really good qualitative, oops, my goodness. Okay, not sure what happened there. Really good qualitative comparison with the experiments. Now, we were one of several teams that tried to reproduce this benchmark, okay? And despite several different models, just about everyone was able to reproduce it, okay? And I would say this is actually not where we want to be, right? Or the benchmark problem isn't being designed properly, or once again, give us enough time and we can calibrate, right? So this has inspired us, right, to recognize the importance of standards and the fact that we need to change things, okay? So my advisor, Ted Belichko, may he rest in peace, okay, back in 1985, introduced an obstacle course for shell elements. Okay, some of you have probably seen this because it's become a standard. If you want to introduce a new shell element, you have to demonstrate that it can go through this obstacle course. Why did Ted do this? Because he was seeing people introduce, again, new shell elements almost every year, fixing one issue and forgetting about the others that you needed to care about. Right? To some degree, we're seeing kind of the same thing in terms of the models that have been developed in computational fracture mechanics, right? So in this spirit, we've introduced a set of challenge problems to assess fracture models. The preprints available in archive. Here they are pictorially, okay? All of these problems have been designed to have three attributes. One, you can test them through standard testing, right? These are well-known problems, okay? The specimen geometries are designed to lend themselves to testing. Some of the problems are incredibly expensive to simulate because of the length scales of the problem and the material length scale that you have to resolve with the model, okay? Two, they lend themselves to a sharp treatment of fracture. So if at some point we have the sharp model that explains everything that we want, we should be able to apply it here. Other ones, there's already a sharp description available, right? Third, they encompass this full range of problems, right? Strength on one hand, crack nucleation, the criticality, Griffith criticality is governed by energetics, mediation between strength and energetics, and then crack propagation in modes 1 and mode 3, okay? Here they are pictorially. If you're interested, you can also listen to the podcast that was about this test, right? Importantly, most of these have been introduced for both a hard material and a soft material. We are providing all of the finite, all of the meshes, hoping people will use them, and the codes, okay? All right, so I think that that's where I'll wrap up, okay? Thank you for your patience. I hope I've kept your attention here after lunch, right? And I'll just conclude by saying, look, the hope here is that if you've properly characterized the material, right, if you know that constitutive information, if you have it, that you can input that to the model and have it be reasonably predictive, right? I think strength has clearly been overlooked, and I hope I've convinced you that it needs to be a focus, and I hope we see models evolve that try to bring in all three ingredients, right? I suspect this is not the final story here, but I think this picture of the competition between strength, energetics, and elasticity is one that we keep in mind as we move forward and introduce new physics, right? Finally, Griffith's incomplete. The question is there a sharp analog to this, right, that also involves strengths, that brings in strength, right? So lots of questions, opportunities in this space for those of you in the community. I think it's opening up more doors than it's closing, and I hope people embrace that. And I'll just leave again if you wanted to catch that podcast on the 9 circles. Thank you very much.
Thank you very much, John, for the fascinating talk. We move to the Q&A sections. Is there any question from the audience?
Yeah, I think John Foster, maybe? Or you could.
Hey, John, nice talk. I think I was at that meeting in Louisiana in 2020 when Oscar was making the case for this, and I'm glad to see where you guys are taking it, so good job. Most quasi-brittle materials, particularly concretes, and they're used in applications where the material is confined. In any kind of confined quasi-brittle material, you always see some kind of post-peak softening due to pore collapse or micro crack, before they actually coalesce to a discrete fracture surface. How do you see this work extending into those type of applications? Is it straightforward?
Yeah, well, so, again, I want to emphasize that what we've developed the theory for here is for materials that are nominally elastic brittle, right? So they do one of two things: they deform or they break, right? Now, concrete is a challenge material from lots of reasons, right? You have the aggregate that you have to deal with. It's not always clear that what you're testing is actually a real material, okay, that where you would expect the macroscopic properties to hold, okay? On the softening side of things, I mean, I think you can think about extending this to include some aspect of micro cracking or something like that you might be able to think about upscaling to affect those kind of behaviors. But to be honest, we haven't really thought too much about trying to move this towards the modeling of concrete. Okay. Yeah.
Thanks for the presentation. Just a quick question. Why is your phase field variable non-symmetric for one of the Brazilian tests? Even if
so great question. So, there's a stochastic element to these tests, right? Because even in the best case, right, experimentally, this is actually not a symmetric problem, right? But when we simulate it, we start off with lots of symmetry, okay? And generally, it's advantageous to perturb the system in some manner, right? So the lack of symmetry that you see there in this particular case is due to the fact that this is brutal crack nucleation. It happens in a single step. And the mesh isn't perfectly symmetric, okay? Now, we've also looked at ways to perturb the system by introducing spatial variations to the tensile strength, right? And that's another way where you can guarantee that as you refine the mesh, you converge on your quantities of interest, okay? But in many of these problems, you find that you have to perturb something, right, as a way to account for the stochastic aspects of strength.
Thank you.
Yep.
Thank you very much, John, for your excellent presentation. I was wondering for the 9 circles, I think it's
a
great idea. So those were computational results, or are those results from experiments? And what kind of material systems do we have all those set of experiments done?
Yeah, sure. Hold on a second. Sorry, it's just a bit slow. So I was showing you simulation results, okay? Some of those are new, right? So for example, that biaxial tension result, qualitatively it resembles what you'd expect, right? Uniaxial tension, brittle materials fail that way under uniaxial tension. Under pure torsion, they tend to localize at 45 degrees, right? This pure shear, you will find experiments for that, okay? Double cantilever beam and the trousers tests, both of those experiments are well known, okay? Single edge notch and tension, experimental results there, okay, that you'll find. This is indentation, lots of experiments, okay? And then the poker chip, that's motivated by experiments as well. Some of these are applicable to soft materials. Some are applicable to hard materials. In the paper, we introduced these tests for two materials, a PU elastomer, polyurethane elastomer, and a glass, okay? So some of these make sense for soft, some for hard, some for both.
Thank you.
Hey, John. Really nice presentation, and I follow your and Oscar's work quite religiously, and I'm very impressed. You guys have made a lot of progress, and we're looking forward to actually learning from it. I also like this 9 circles idea, and it's nice to have the complete set of so we can try out new models. I have one comment about the writing of the energy-based methods for fraction. For soft materials, I totally agree that if it's incompressible material, there's no energy in the hydrostatic tension. But there's no material that is ideally incompressible. They are nearly incompressible. If you take a soft material that is 0.49999 Poisson's ratio, because the bulk modulus is 3 orders of magnitude more than elastic modulus, even for very small volumetric strain, you get a very decent amount of energy. So I don't think that argument should be used to write off the energy-based methods. The other thing I like, the strength-based methods is very nice, but the stress is incorporated in a lot of these energy calculations. So in a way, there are other methods, maybe not as good as the strength-based method, but they are not completely off the track. So we need to keep our mind open, look for those other methods, see how they evolve.
So I missed the second part, but let me address the first part, right? So, you know, of course you're correct that real materials aren't perfectly incompressible. There's always a little bit of incompressibility there, right? And, you know, all the developments here, right, they started with trying to explain experiments on real materials that were nearly incompressible. So even though the incompressible limit makes the point, the nearly incompressible materials are just as problematic. What you find is that energetic methods vastly overpredict the hydrostatic strength of even nearly incompressible materials. Okay. The real issue is that, you know, you don't have any control over the hydrostatic strength in a lot of these models because it's just not an input, right? A lot of the models that we've used have just relied on a specification of the uniaxial tensile strength, and that's it, right? And the fact of the matter is that how things get loaded, right, in general can vary quite a bit, even within the context of the same problem, right? As the cracks evolve and stress fields change, you might be activating one port of the strength surface at one instant in time, but another just later on. And so if you don't have that representation built in, right, you're stuck in this spot of calibration. Yeah.
Okay. Hello. So your model has a failure stress envelope.
Yeah.
Which is necessary because, you know, as the experiments show.
Yeah.
Previously, you've developed cohesive models that have a failure energy in some sense, which you can interpret as a stress. And of course, they don't vary with the biaxiality, so they're not appropriate. But the terminology around those is that they're cohesive, right? Because they have a sort of an independent failure stress and an independent Griffith energy.
Yeah.
But you don't use those terms for this model. I was just kind of curious how you're making the distinction between sort of those cohesive ones and this one.
So some of you might remember the talk I gave in New York City where we were working with the cohesive models. And what always bothered me about the phase field models at that point in time was this notion that the regularization length had to be set, right, to the material. Why did it bother me? Because, first of all, you're breaking the gamma convergence connection, right? I mean, I don't care too much about that, but if you're setting epsilon as a material parameter, you have to admit that you're not using a regularization of any sharp model, right? But, so what I liked about the idea introduced by Eric Lorentz was here was a way to essentially isolate the regularization length from the apparent effective uniaxial tensile strength that the model will give you, right? So that you could think about lowering epsilon, which is useful in lots of ways, right? The problem is that those models are still fundamentally energetic, right? And you're at best being able to prescribe the strength surface, match it at a single point. And that's just not, that's a good, it's not a terrible place to be, but it's definitely not going to give you the full fidelity that you want in general.
Yeah, but the point is that the new model has both those properties.
It does. So I mean, cohesive has a very particular connotation to it within the community, and this is trying to avoid any kind of confusion about exactly what it is.
Gotcha.
Right.
Okay. Thank you. Let's thank the speaker once again. Thank you, John, for the excellent talk.
Thanks.